Hi everyone, welcome to Food for Thought Chemistry. Today we're going to be talking about atoms and bonding. Last time we talked about the particles that make up an atom. So we have protons, neutrons, and electrons. Today we're going to focus more on electrons. So we know that atoms carry their electrons around the nucleus. But where do they carry them? Electrons are particles that can fly around and move wherever they want, but there are certain areas in which they will be more likely to congregate. So we call these orbitals. The orbitals have different shapes, and the main ones we're going to be discussing are s orbitals, p orbitals, d orbitals, and f orbitals. So you can see we have different shapes, and as you go from left to right, the orbitals get bigger and more complex. So there are up to 1 s orbital, 3 p orbitals, 5 d orbitals, and 10 f orbitals in any given level. So for any given atom, there are what we call energy levels. The energy levels feel like this. So say we're going to be at the 4th energy level, so n equals 4. And I'll explain what this n means later. So first we're going to have the 4s, then we're going to have the 4p, then we're going to have the 5f, if there's anything in there, then we're going to have the 4d again. So the levels fill from lowest to highest energy, which is what we call the Aufbau principle. And Aufbau just means building in German. So we're building up the energy levels. So in each lobe of an orbital, we can have up to 2 electrons. So thus, in an s orbital, we can have 2. In a p orbital, we can have up to 6. In a d orbital, we can have up to 10. And in an f orbital, we can also have up to 10 electrons. So let's give a little example here. If we have sodium, which is going to have the symbol Na, is number 11. So it has 11 electrons because it has 11 protons and we need to be neutral. So we're going to have 1 s2, 2 s2, 2 p6, and then 3 s1. The d and f orbitals only appear later. So if we were going to have, say, something with number 23, would have 1 s2, 2 s2, 2 p6, 3 s2, 3 p6, and then we're going to have 4 s2. And see, this is 20, so then we'd have 3d3. All right, so now we're going to talk more about these energy levels. So what we're going to have are called the quantum numbers. And these are going to describe every single electron in an atom. So first we're going to have n, which is the principal quantum number. And this is just what energy level we're in. N can go from all of the natural numbers. So that's 1, 2, 3, 4, so on. Then we're going to have L, which is going to be the magnetic. And this tells us what kind of orbital we're in. So it goes from 0 to, it actually goes up to 7, but we're just going to deal with up to 3 for now. And so an S is going to be L equals 0. A P is going to be L equals 1. A D is going to be L equals 2. And an F is going to be L equals 3. Then we're going to have ML, which is going to be like the magnetic quantum number within the orbital. So each orbital, the S is just one of them, but the P actually looks something like this. So we have 3 P orbitals, Px, Py, and Pz, for each axis in the 3-dimensional coordinate plane. So the Px is going to be L equals -1, ML equals -1. The Py is going to be ML equals 0, and then the Pz is going to be ML equals 1. And we can do that so on and so forth for the d and the f orbitals. So they go from negative something to something so that the total number of them is going to be equal to L. And then finally, we're going to have the ms, which is going to be the spin quantum number. And what this tells us is the spin of an electron. So we know we have 2 electrons per lobe. And they're going to have different spins. So ms is always going to equal plus or minus 1/2. And we can denote the spin in terms of arrows. So for instance, if we wanted to have a p orbital, so let's call this, I don't know, 2p5. So we have our 3 lobes. And what we're going to do is we're going to try to fill each lobe with only 1 electron first. So we're going to have 3, because 1 for each lobe. And then finally, we're going to put in 2 more electrons, because we need to make 5. So then we'll put the ones with the negative spin. And we can use this box notation as well as the superscript notation up here to denote electron configurations. Now, what we have are called valence electrons as well. And these are going to be in the highest energy level. So for instance, in sodium, our valence electron is going to be in the 3s1 suborbital. It's going to be in the 3s suborbital. And note that there's only 1 electron there. So sodium has 1 valence electron. As you go left to right across the periodic table, the number of valence electrons increases. And that's going to tell us about bonding. So valence electrons are used for bonding. We can denote where the electrons are by means of a Lewis structure. So, say we're going to have the molecule CO2. So we're going to have carbon. Carbon has 6 total electrons, so 2 are going to be in the 1s orbital, so it gives us 4 valence electrons. We only denote the valence electrons in a Lewis structure. Then we're going to have an oxygen on either side. Now, oxygen has 6 valence electrons because its configuration is 1s2, 2s2, 2p2. So we're going to have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. And this would be our Lewis structure for CO2. Next time, we're going to talk about more complicated Lewis structures, as well as VSEPR, which will tell us the shapes of molecules. Join us.